A little over a year ago, I made a series of videos where I converted aspirin to Tylenol. For those of you outside of North America, Tylenol is probably known as acetaminophen or paracetamol. The brand aspirin seems to be pretty universal around the world, but it might also be known as ASA. I think the idea of converting one pain relieving drug to another is quite interesting, but I don't think I did the best job at conveying that because the original series was spread out over several videos. So I've decided to make a single summary video which covers the entire process that I did. The reason why this conversion is even possible is because both of these medications are based around the same core molecule called phenol. What this means is that if I'm able to degrade one of them back to phenol, I can then build my way up to the other one. This is the pathway that I came up with, which started with aspirin and was based on reactions that I knew would work. I decided to start with aspirin because breaking it down to phenol and then back up to Tylenol is relatively straightforward. The other way is possible, but it's significantly harder for both the degradation and the synthesis parts. In any case, with that being said, we can get things started. The first step was to extract the actual aspirin from the pills, which is chemically known as acetylsalicylic acid, or ASA for short. In total, I used 200 pills, which only contained 100 grams of aspirin. The rest of the stuff in there is just a bunch of filler junk. To have an efficient extraction, the pills need to be powderized. It is possible to do this with a mortar and pestle or a hammer, but it's a pretty big pain. I generally find that the easiest method to crush pills is to just use a coffee grinder. All the pills were added in several batches, and each time the powder was transferred to a beaker. Then on top of this, I added 200 ml of acetone and turned on the hot plate. The aspirin readily dissolved in the hot acetone, but the other junk didn't. I brought it to a boil for several seconds, and then I filtered it off. The solid stuff left in the beaker and whatever was caught by the filter was then washed with another 200 ml of boiling hot acetone. This was done to just really make sure that I extracted as much as possible. In the flask, some of the aspirin started to precipitate as the acetone cooled down. With just a little bit of mixing though, everything goes back into solution. Now, to isolate the aspirin, I just needed to get rid of the acetone. It is possible to just pour it out and let it evaporate on a dish, but I decided to do the more proper method and do a distillation. I cranked up the heat, boiled off the acetone, and collected it in the flask on the right. In the original flask, I was left with nearly dry ASA, but there was still a bit of acetone left. To get rid of the last bit, I could have set up the distillation again, but I decided to just pump it on my vacuum. I ran it for about 10 minutes, and it didn't completely dry it up, but it was a lot better than before. Just as a final purification step, I decided to do a recrystallization. It was transferred to a large flask, and then I dissolved it in a minimal amount of boiling water. There were some gooey bits floating around in it though, so I had to filter it off. I just passed it through a coffee filter into another large flask, and then I took it off the hot plate. As it cooled, its solubility in water slowly decreased, and it crystallized out. Once it was room temperature, I put it in the fridge for a couple hours, and then filtered everything off. The aspirin was washed a couple times with ice cold water, and then everything was transferred to a piece of paper to dry. The final recovery was 94 grams, which was extremely close to the theoretical 100. It is possible to get 100% recovery here, but because I recrystallized it, some of it stayed dissolved in the water, and that's probably where I lost most of it. Okay, so now that the aspirin's been isolated, it's time to get started with the actual synthesis stuff. The first thing I needed to do was convert it to salicylic acid. Unfortunately, I didn't have a single flask that was large enough, so I had to do the reaction in two separate batches. Into each of them, I loaded 47 grams of aspirin, 650 ml of distilled water, and 12 ml of concentrated hydrochloric acid. The acid I'm using was just picked up from a local hardware store. I put one of them in a heating mantle and cranked up the temperature. Above the flask, I also connected a condenser column to recondense any water that escaped. As the mixture heated up, the aspirin slowly dissolved and I was eventually left with a crystal clear solution. When it got to the boiling point, I turned on my timer and I continued boiling it for 30 minutes. The reaction I'm doing here is known as an ester hydrolysis. Aspirin's chemically known as acetylsalicylic acid, and under these hot acidic conditions, it's broken apart to form salicylic acid and acetic acid. This reaction's in equilibrium though, which means that the products can react with themselves to reform the starting material. As a result, the reaction doesn't truly go to completion, and there's still a bit of starting material left over. However, by including a huge excess of water and heating things, it's possible to severely hinder the backwards reaction. Under these conditions, it usually goes to like a 90 or 95% completion. Anyway, after the 30 minutes, the heating mantle was removed and the process was repeated for the second flask. As the second reaction was heated up, the other one cooled and nice salicylic acid crystals started to form. After I refluxed the other flask for 30 minutes, I let it cool and I waited for the crystals to form in this one as well. When both of them had gotten to room temperature, I filtered off the crystals. They were all washed with some ice-cold distilled water and dumped onto a piece of paper to dry. The final yield was 62.6 grams, which was 87% of the theoretical. To get the overall efficiency of the process so far, I just need to multiply the efficiency of each completed step. So I multiply 0.94 by 0.87, which gives me 82%, which isn't bad. With every step though, unless they're 100% efficient, this number's going to go down, and just one inefficient step can be quite devastating. When I first made this video, I predicted that the final efficiency would be around 30%, but that was way too optimistic. You guys will see just how far off I was. The next step is to convert the salicylic acid to that common precursor called phenol that I talked about earlier. What's nice is that no other chemicals are required to do this, and all I need to do is heat things up. All the salicylic acid was dumped into a flask, and I set up a short path distillation. I forgot to put in a stir bar earlier, so I quickly dropped one in. Then I turned on the stirring and I cranked up the heat. The salicylic acid quickly melted, and I was left with a dark liquid. Pure salicylic acid is colorless, and the darkness is due to impurities. This is okay though, because this step's gonna clean it up anyway. The major thing going on here is a reaction known as a decarboxylation. As the salicylic acid is heated, this carboxylic acid group that I've marked in red breaks off as carbon dioxide gas and leaves behind phenol. At the same time, there are a bunch of side reactions happening as well. Some of the salicylic acid reacts with phenol to form phenyl salicylate, which then reacts with itself to form a bunch of other side products. The major result of this is a loss of product and a diminished yield. So although this process is easy to do and works quite well, it's not very efficient. The phenol that doesn't react with salicylic acid is boiled out of the flask and collected in the one on the right. The most important part of this process is keeping the heat high and preventing the phenol from crystallizing in the apparatus. Its melting point is around 40 C, so it was important to keep the glass hotter than that. If any phenol did start to freeze in it, it's pretty easy to fix, and I just had to blast it with a heat gun. The boiling point of phenol is 182 C, and everything below this temperature was collected. The moment the temperature started to rise above this point, the distillation was stopped. Left in the reaction flask, there was a bunch of polymerized black tar, which I just disposed of. The phenol product I got was colorless, but it still had a bunch of water and other impurities in it. The major sign of this was that it didn't crystallize even when it cooled to room temperature, which was well below its freezing point. So just to clean it up, I distilled it again. Initially, some milky white stuff came over, which definitely wasn't pure phenol. It was probably an azeotrope of water and phenol, and maybe some other stuff. I just waited until the stuff coming over was at about 180 C, and then I swapped the flasks. I collected everything between about 180 and 183 C, and when the temperature started to rise, I stopped the distillation. This time, as it cooled, it crystallized into a solid chunk. I used the heat gun to warm it up and remelt it, and then I transferred it to a container. The final yield was 21.8 grams, which represents a percent yield of about 51%. This isn't exactly the best yield, but as I said, the process isn't super efficient, but it is easy. In any case, this was the first big hit to the overall efficiency, and it brought it down from about 82% to 41%. Okay, so the degradation part is done, and it's time to start building it up to Tylenol, aka paracetamol or acetaminophen. What I needed to do was tack on a nitro group to the phenol by carrying out a nitration reaction. I started by making the nitration solution, which first involved dissolving sodium nitrate in water. Then, I very carefully added sulfuric acid. It was important to do this slowly and to also use an ice bath because it generated a lot of heat. As the sulfuric acid was added, it reacted with the sodium nitrate to make nitric acid. An excess of sulfuric acid was used here so that the final result is basically a mixture of nitric and sulfuric acid. In theory, I could have just directly mixed nitric and sulfuric acid, but at the time, I didn't have any nitric. All of the phenol was removed from its container and transferred to a beaker. I then poured in 5 ml of water and I put the beaker in some hot water to melt it. The water was added here to prevent the phenol from freezing again once it was removed from the hot water bath. When the phenol had completely liquefied, I poured it into an addition funnel that was positioned above the nitration mixture. I opened the addition funnel and I started adding the phenol dropwise. You can immediately see some brown stuff forming. This whole reaction is kind of a dirty mess, and this was just the beginning of the nightmare. Anyway, this was the reaction that was going on. As the phenol was added, it was nitrated to form two products, orthonitrophenol and paranitrophenol. The one I wanted was the paranitrophenol, and the ortho one was just a side product. Keeping this reaction cold was extremely important because I only wanted to add one nitro group.
If the temperature were allowed to increase too much, it might have started forming di- and trinitrophenol, which I definitely didn't want.
As the phenol was added, the solution got darker and darker. When I was eventually done adding it all, I covered the top with some plastic wrap and I let it stir for 2 hours. When I came back, it had partially solidified and there were some nasty black chunks in there. I added 150 ml of water and then I ran the flask under some warm water to melt everything. I very carefully poured off the upper red water layer and I tried to keep the black lower layer. The goo that remained was washed again 3 times with 50 ml of water. The nitrated phenols are nearly insoluble in water, so they shouldn't really be washed away here. All of this washing was really just to get rid of unreacted phenol, acid, and some other side products. Because I used cold water for the washings, things started to solidify again. I probably should have just remelted it, but I instead tried transferring it as a solid to the other flask. I was able to use up to 250 ml of water to help me out, but it was still a major pain. With everything transferred over, the mixture was set up for a distillation. As the water was boiled off, the yellow orthonitrophenol was carried over with it. Once I collected about 150 ml of water in the flask on the right, I added 150 ml more to the boiling flask and continued the distillation. Near the end, the condenser started getting all jammed up with solidified O-nitrophenol. To fix this, I just turned the water pump off and I let the water stagnate in the condenser. Without a fresh supply of cold water cooling things, the hot water vapor was allowed to travel down the condenser and it slowly cleaned things up. Eventually, the water coming over was crystal clear and there was no yellow tinge to it. At this point, the distillation was done, so I turned off the heating and I dismantled the apparatus. On the left is the original boiling flask, which still contains my desired paranitrophenol. On the right is relatively pure orthonitrophenol mixed in with water. They were both still quite hot here, so I let them cool to room temperature, and then I left them both overnight in the fridge. In the morning, I quickly filtered off the orthonitrophenol and washed it with some water. Then, I transferred it to a piece of paper to dry, but I didn't really have a use for it, so once it was dry, I just put it away in storage. When I took a look at the other flask, I was happy to see that some crystals had formed. Unfortunately, though, there was a solid tar chunk at the bottom that I had to deal with. Most of it was probably garbage, but some p-nitrophenol was mixed into it. I filtered off the crystals and the tar separately, but I ended up combining them anyway. Into the flask, I added about 1 gram of activated charcoal, which is good at picking up colored impurities. On top of this, I poured in 100 ml of 2% hydrochloric acid. Then I brought it to a boil and kept boiling it for about 2 minutes. I filtered off the activated charcoal, and I did my best to leave the tar at the bottom of the flask. Some of it was still transferred over though. I let the flask cool to room temperature, and then I placed it in the freezer. When I took it out, I was really happy to see that a bunch of nice crystals formed.
I vacuum filtered off the paranitrophenol, and I left the tar at the bottom of the flask. All of the water was pulled through, and I washed the crystals a couple times with some ice cold water. The product that I got here wasn't super pure, but it'll be cleaned up in the next couple steps.
The final yield was extremely low, and I only got 1.82 grams, which is a 6% yield, so not exactly amazing. The yield of the orthonitrophenol was much better, but it was still only 25%.
Although this reaction wasn't very efficient at all, I think in the end it still was the easiest way for me to do it.
Anyway, with the crazy low yield of this step as well as the last one, the overall process efficiency was knocked down to a killer 2.5%.
Moving on, the next step was to reduce the nitro group to an amine, which is NH2 instead of NO2.
There are several ways to do this, but I decided to use the sodium borohydride and palladium on carbon method. It just seemed to be the cleanest and easiest.
Into a flask, I added 0.75 grams of sodium hydroxide drain cleaner, followed by 18 mils of water. I dropped in a magnetic stir bar, turned on the stirring, and waited for it all to dissolve. When I had a nice clear solution, I dumped in 1.01 grams of sodium borohydride, and I stirred this until it all dissolved as well. Then, on top of all of this, I added 90 milligrams of palladium on carbon catalyst.
I cooled this mixture to 13C, and I slowly added the p-nitrophenol in small portions. The addition generates a bit of heat, and it's important to keep the temperature as close to 13C as possible. Sometimes the temperature started to get too low though, and I had to take it out of the ice bath. Then, when it started to heat up again, I just added it back. The reaction I'm doing here is generally known as a reduction, where the p-nitrophenol is being converted to p-aminophenol. The sodium borohydride acts as a carrier of hydrogen gas, which is catalytically released by the palladium on carbon. The palladium on carbon then acts again to catalyze the actual reduction reaction between the hydrogen gas and the p-nitrophenol. If you look closely, you can see there's quite a bit of bubbling going on, which is all the hydrogen that's being generated. For those of you who are wondering, palladium on carbon is basically just extremely small particles of palladium stuck onto bits of carbon powder. This makes a very small amount of palladium have a huge surface area, which is much more efficient than just adding solid palladium metal. On top of this, it's also a lot cheaper. After everything was added, I washed the sides of the flask and the thermometer with a small amount of water. I then continued mixing it for another 30 minutes. When I came back, all of the solid p-nitrophenol had disappeared, and the solution had become completely black. The reaction was done at this point, and I started to slowly add 28 mils of dilute hydrochloric acid. This decomposed any unreacted sodium borohydride and converted it to boric acid, sodium chloride, and hydrogen gas. It also reacted with the p-aminophenol itself and converted it to p-aminophenol hydrochloride, which is much more water-soluble. This reaction caused a lot of bubbling, and I was afraid it would overflow, so I transferred it to a beaker. I continued adding the rest of the acid, and it eventually stopped bubbling. I used some universal pH papers, and I saw that it was around 1, which is highly acidic and exactly what I wanted. To get rid of all the carbon that was floating around, I just filtered it off. Some of the carbon managed to make it through though, so I filtered it again. Unfortunately, the whole filtration process took quite a long time, and the p-aminophenol in it started to decompose and the solution became purple. P-aminophenol is quite sensitive to light, so this step should really be done as fast as possible. In hindsight, I probably should have done a vacuum filtration instead. Anyway, to get out the p-aminophenol, all I had to do was convert it back to its free base form, which isn't very soluble in water. To do this, I just needed to carefully add baking soda and make sure it didn't bubble over. At some point, one of the additions caused a very distinct color change, and this told me I was close to the neutralization point. With only a bit more baking soda, the solution started to become cloudy because p-aminophenol was precipitating out. I kept adding small amounts, and I knew it was done when it didn't result in any bubbling. I tested the pH and saw that it was around 7, which was perfect. The product just needed to be filtered off, and again, I did a gravity filtration. I really should have done a vacuum one though, because the degradation here is quite significant. I washed the product with a bit of water, and then it was allowed to dry. To try and limit its decomposition, I turned off the lights. After a few hours, I scraped it off the filter paper, and then I left it out for a couple more hours. When it was totally dry, I weighed it, and the yield was 0.82 grams, which is a percent yield of 58%. So now the overall process efficiency is about 1.5%. Okay, so this brings us now to the final step. All the p-aminophenol was added to a flask with a stir bar, and I poured in 7.4 mils of water. I turned on the stirring, and when I had an even suspension, I added 0.9 mils of acetic anhydride. Immediately, almost all the p-aminophenol disappeared, and the solution became a dark red-black color. The reaction that's going on here is an acetylation, where the p-aminophenol is reacting with the acetic anhydride to form Tylenol. It also produces acetic acid as a side product.
Its generic chemical name is based on its structure, and it's called paracetamol. The brand name Tylenol and most of its common names are derived directly from it.
About 5 minutes after the acetic anhydride was added, the acetaminophen started to precipitate from the mixture. I then mixed it occasionally over the course of about 15 minutes. When the reaction was done, I added it to my filter funnel and I turned on the vacuum pump. I washed the flask and the acetaminophen a few times with cold water. The powder I was left with was dark and dirty, so it needed to be cleaned up. I put it all into a small flask and added a bit of activated charcoal. I poured in a small amount of water, mixed it around, and turned on the heating. When it started boiling, I set things up for a hot filtration, and I filtered off the activated charcoal. I needed to do a hot filtration here because the water in the flask was close to saturated with acetaminophen, and if it cooled too much while filtering, it could crystallize out and mess things up. By having water boil under the funnel, the steam that's let off keeps everything nice and hot. When everything had passed through, I washed the flask with a small amount of boiling water. Then I kept everything on the hot plate for just a little while longer to boil off some of the water and concentrate the solution. I took it off the hot plate and let it cool, and crystals of acetaminophen started forming, but they were still off color. So I filtered them off and did 2 more recrystallizations using activated charcoal. After the last one, I was left with some nice and clean-looking crystals. The final yield was 0.21 grams, which was less than the amount that would go into a single regular-strength Tylenol tablet.
So basically, I was able to convert 200 extra-strength aspirins into one really weak Tylenol.
The percent yield of this step was extremely low, at around 18%. I probably lost most of my product doing the multiple recrystallizations. In a couple of them, I think I used a lot more water than I actually needed. In any case, this puts the final efficiency of the process at an impressive 0.26%. So my original prediction of 30% wasn't that far off, I just kind of misplaced the decimal by 2 spots. Just to confirm that really this was in fact acetaminophen, I did a melting point test and it was almost exactly the theoretical.
I also ended up doing one other quick test. I transferred a small amount of it into a vial, added some water, and shook it around. I then added a couple drops of ferric chloride, and there was immediately a small color change. This test is simply known as the ferric chloride test, and a positive result, like we have here, indicates that a phenol group is present. And since Tylenol has a phenol group in it, this is a good sign. The result from this test, along with the melting point, didn't definitively prove that this was Tylenol, but it was extremely unlikely that it could be anything else. I wanted to be 100% certain though, so I sent a sample to my friend and he ran a proton NMR. The graph that was generated matched perfectly with acetaminophen, and it was also pretty clean. This tells me the product that I have is relatively pure, at least in terms of organic impurities. There could in theory be some inorganic stuff in there that I just can't see, but I don't really think that's likely. In the end, this project was mostly just for fun and to see if I could even do it. I do think the idea of converting one drug to another is cool, but I think the whole idea of planning and designing my own pathway is even cooler. Even though I do stuff like this all the time, it still blows my mind that it's possible to systematically build and degrade things on the molecular level. I hope you guys liked this video in general, and that it gave you insight as to what multi-step organic synthesis can be like. Synthetic pathways like this are extremely common in industry, and they're used to produce most drugs, as well as many flavorants, vitamins, and supplements. In the future, I plan to do another project like this, where I synthesize caffeine. I think it's also something like 6 or 7 steps, but I won't be posting it as a series, and I'll probably make it into a video like this. Or maybe I'll split it into 2 parts if it gets too long.
As usual, a big thanks goes out to all my supporters on Patreon. Everyone who supports me can see my videos at least 24 hours before I post them to YouTube. Also, everyone on Patreon can directly message me, and if you support me with $5 or more, you'll get your name at the end like you see here.